All right, so now we're going to talk a little bit more about balancing nuclear equations. Balancing nuclear equations are pretty easy. They're not very difficult at all. All you have to do is work slowly, and they come pretty easy. So first, let's talk about the two different groups of nuclear reactions. One group of nuclear reactions is called an emission. Some examples of that may be an alpha emission or an alpha emission. Sometimes they don't say alpha particle, but they'll an alpha emission. Or you could have a beta emission. You also could have a proton emission, a neutron emission, a positron emission, and another word for emission is decay. So I could also have like a positron decay. All of these things fall under the group of emissions. Okay. What's special about emission is whatever this particle is, that particle is in the product. Okay, so if it's an alpha emission in the product side of a reaction, you're going to see the particle. If it's a beta emission, you're going to see a beta particle in the product. If it's a positron decay, you're going to see the positron in the product. The other group is a capture. So for a capture, same deal. You can have an alpha particle capture, an alpha capture. You can have a beta capture. You can have a positron capture, a neutron capture. There's a whole different ways that you can have captures, but the big deal here is that the particles is in the reactant. So let me show you what I mean. I have two different thorium atoms, right? And in the first thorium up here, we're going to make this an alpha emission. Now, by definition, an alpha emission means that the particle is in the product. So if 230 thorium is undergoing an alpha emission, it will have the alpha particle in the product. Okay? We don't know what else it made yet. We haven't figured that part out. Now, if it is an alpha capture, we're going to have that same alpha particle in the reactant. Also remember that an alpha particle can be written in more than one way. We can write an alpha particle with a 4,2He, 2 plus, symbolizing that it is a helium nucleus. Remember, this is the only element that will make an alpha particle. The only one. All the other ones won't make an alpha particle. But a helium, if I just have the nucleus, that means no electrons, that is the same as an alpha particle. Sorry about that spelling snafu there. All right, so let me show you how to solve these. So whenever you have an alpha emission or an alpha capture, you kind of set up the problem so that you're looking at all the top numbers together and all the bottom numbers together. Wherever your arrow is, that becomes your equal sign. So looking at the top numbers, I have 230 equals 4 plus x. In order to solve this, I will need to subtract 4 from each side, and that will give me 226 equals x. Okay, so most of you are good with that one. That makes sense. So that tells me that the top number in my problem should have been, my mass number, should have been a 226. Now we're going to work that bottom out. So the bottom, we have 90 equals 2 plus y. Subtract 2 from both sides, and I wind up with 88 is equal to y. When I set up my problem, my final answer is going to be 230, 90 thorium, arrow, that there alpha particle, plus 226 on the top, 88 on the bottom. And in order to figure out what element that is, I have to go to the periodic table. And I'm just going to look for the element that has 88 as a mass number. And if I look carefully, I can find that right there. So radium has a mass number of 88. Remember, the proton number, the number on the bottom, always defines the atom. So I'm going to put Ra, put a box around it, and I'm done. I've just written an equation for the alpha emission of thorium-230. Now let's look at the alpha capture of the same particular substance. Okay, so for this one, I'm going to rewrite that since it's got a lot of dots on the page. So we have 230, 90, thorium. And we talked about the fact that an alpha capture means that the alpha particle is going to be in the reactant side. We're going to figure out what we're going to get. Now, these are a little bit easier. So we have 230 plus 4 equals X, and that would be 234. I'm going to do the same thing again. 90 plus 2 equals 92. Now, I'm going to rewrite the problem. 230, 90 thorium plus 4, 2 alpha gives me, I'm going to look for the atom that has 92 in its atomic number. So 92 is uranium right there. Do not focus on the mass number, or rather the average atomic mass, since this is the decimals. That is not what has to match. What has to match is that whole number, the number of protons. Remember, protons determine the identity of the element. And we're done. Ta-da! So you now have a formula for an alpha emission and for an alpha capture. If it is a beta particle, you would just put a beta in wherever you saw an alpha. If it is a positron, you would put a positron in. Same exact math. I also want to point out that this problem could also be written like this, because this and this are the same thing. Remember, an alpha particle kind of has two different ways that you can write it. You can write it with He and a 2 plus, or you can write it with the alpha symbol. Okay? I hope that helps, and we'll talk more in class.